Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Can I get a show of hands of the people who would count themselves as machine learning types? Oh, excellent. And programming language types? We have about half and half, which is exactly what I wanted. Very, very cool. All right. So, yeah, I am going to talk about the gap between our two research areas, or the gaps, plural. I'm not really clear on that in the slides, I guess, but and how to close them and bridge them. I also want to illustrate probabilistic programming a little bit. This what we usually call an intersection between machine learning and programming languages, and that the gaps are actually both technical and cultural. So why? Because everybody knows we have a hard time working together, and I have not seen anybody or any classification of the reasons why. Anybody compile, the kinds of put together, information on the kind of attitudes and things that cause this are problems. I've heard that from like 4 people now. Yeah, it's a dangerous talk. So can I have everybody's participation for just a little bit? I would like you to look to your right, to the neighbor on your right, and look to the neighbor on your left. Okay, thank you. I'm going to mischaracterize and possibly offend both of these people. But not you. So I've been thinking for a long time about how to present information like this, and I think it's best done by telling my story. I was born at a very young age. No, we don't really need to go that far. We can just go to the end of my master's research. I was fortunate to have an advisor who counted pretty much any kind of solving difficult under-constrained problem as machine learning, and that included computer vision. So he basically let me do what I want. That was really cool. So what I worked on was super resolution, and how I did it was by making a Bayesian model. The model would allow me to take a low-resolution image and infer a scene that could have generated this image using a known capture process, and then it would simulate taking a picture with a better camera, maybe a higher resolution camera. As a Bayesian model, it looks like this. And the objective was then to get a sample from I prime given the given image I. This is the math that the model describes here. And I still think it's beautiful. One of the reasons I think it's beautiful is that it's utterly reproducible. The only thing that's really kind of missing is this H function here. Happens to be a blurring function. It's in the paper. But, I mean, given this, and H, and a few tips on how I did inference, you could completely reproduce what I did. It's kind of one of the hallmarks of doing Bayesian inference. But the code to implement the math was not as beautiful. It was 600 lines of evil Python, and Python's really not supposed to be evil looking when you're finished with it. However, I got some good results. Here was my main competitor. I had identified some areas where I thought we could do better. So in the gradients here, there's some stepping, and along the edges, it doesn't look quite straight. And my algorithm didn't have those problems. And it also beat the state of the art on some objective measures. Quote unquote objective. I had a co-author who pestered me endlessly about doing this. So he said, Bayesian inference, this is really good at missing data problems. And super resolution is like a missing data problem, right? You're filling in the pixels that are missing. So why don't you try CCD demosaicing? I'm like, what is that? So what it is in a consumer camera, over the CCD array, there's a Bayer filter that filters out light. And so the pictures that as a consumer camera actually look like this. The red, green, and blue are not all in the same position. So they have to be demosaiced, or there has to be some interpolation that goes on to fix that. And so with very, very few changes to the code and no changes to the model, I was able to do it. And it comes up with some lovely sharp edges and very few artifacts. In painting was another thing he suggested. Mark all these things as missing that are over the top of the image and run very similar algorithm and exactly the same model, and it just sticks them all back. It misses some details. It just puts plausible things in. So it only looks like magic. It's not magic. It is what happens when you model something as precisely as you can using a framework that is tolerant of uncertainty. It was really only mostly satisfying. I'm still not sure the program is correct, for example. And it's not just because it was long, it's because every time the model wasn't something that I just made up one day and tried. It's something I iterated on over and over again. I think I tried 50 versions of it. And every time I made a change to the model, I had to make a change to the code to keep them in sync. And that's just, the opportunities for errors there are just rife. The other problem was I could not model things the way I wanted to. In real life, objects occlude each other. When they occlude each other, there is a sharp discontinuity. The thing that makes anti-aliasing happening, the smoother edge, is blurring by the lens. And I could not figure out how to make that happen. Here's the fine print from the paper that makes it sound kind of like a good thing. But without the fancy talk, we can't figure out how to model blur as part of image capture, so we hack it into the scene model. Dissatisfying. Well, I heard a programming language professor, Jay McCarthy, was coming to BYU. I sent him an email and asked him to take me on. I was kind of ready for a change. And it took me an embarrassingly long time to come up with this idea. 6 months. Hey, I could use this to fix my old problems. You see, if I had a compiler for a probabilistic language, then I wouldn't have to write the code, right? It became clear very quickly that we had communication issues. I love this comic. Now, human beings, I think, have it better than dogs because we can fill in using context. However, if we think we already know what the words mean, we still have some, it might lead to greater issues. So Jay would say something like, the Curry-Howard correspondence is only a general observation except in the calculus of inductive constructions in similar languages, and I would hear Indian cuisine correlates with integration and possibly something about making learning algorithms. Wait, where? So all this comes from Indian cuisine. That's currying, obviously, correlates, correspondence, integration, calculus, making learning algorithm. Oh, inductive, right. So in machine learning and programming languages, we use the word induction and inductive in very different ways. So I would say something like Metropolis-Hastings algorithms are inherently sequential because they step according to a distribution conditioned on their last location. And Jay would hear, you can't parallelize algorithms for walking around in cities, and possibly something about hair care. Right, we talk past each other a lot, and this is just vocabulary. So this is where the gaps come in. Our two cultures are separated by fairly wide gaps, and the formalisms that we use and the math that we use, they're separated by some fairly wide gaps too. And some of these make it pretty hard to work together. So my objectives today are to identify the major ones, to classify them as technical or cultural, and show how to bridge or close them. Because I've had some experience doing this, and I want to pass it on. So, first gap, vocabulary. So PL theorists are kind of like the Inuits of North America. They have 30 words for snow. We have 30 words for meaning. And, well, to be fair, they actually have a language where you can smash a bunch of words together to make new ones. That's kind of like Finnish. So these are the ones I came up with off the top of my head. Now, again, to be fair to us, we usually postfix this with semantics. Semantics just means meaning. But yeah, we have a lot of words for the thing that we do. This is the major thing that we do. The word we use depends on a lot of fine distinctions that somebody from the outside really doesn't know or even care about sometimes. Oh, no, usually. So usually these days I just stick with denotational and operational, and when that's not enough, it's the meaning of programs as the values they reduce to, the meaning of programs as mathematical functions, the meaning of programs as probability distributions. Now, in the machine learning side, just the statisticians have 30 words for distribution, which is the thing that they work with all the time, or the Bayesians. And those are the ones I came up with off the top of my head. There are a lot of them. And again, the word that you use, it depends a lot on a bunch of fine distinctions that an outsider really doesn't know about or care about. So I usually just stick with distribution and conditional distribution nowadays, and that seems to work just fine. And if I have to, I get more precise. The distribution of the parameters given the data, the distribution of the things I haven't seen given the things I have seen. Now, this vocabulary refers to even stranger mathematics. Now, to somebody who is familiar with Bayesian inference, this may not be perfectly legible, but it is at least decodable. See, as soon as you see that little tilde right there, you can start working out what it is. The only thing that might be a little odd is this, which is a potential. I was mixing Markov random fields with generative models. This is the kind of thing you would see from programming languages, and if you're used to reading denotational semantics, this is, again, decodable. The only kind of odd thing is that these are defined in terms of an arrow calculus, which is not a typical thing to do, but it's totally allowable. To close this gap, the only real option we have is to take some time to explain to each other what these things are. I have some tips about how to do that. So, explaining semantics to somebody from machine learning. Here are some things to avoid, which are probably the most interesting things we make semantics about. That's kind of annoying, but yeah, okay, lambdas, continuations, type systems, no. Avoid philosophy. Do not say this sentence, okay? Programs mean nothing until the language has a semantics. Mathematically, strictly speaking, yes, that is true. But if you say that to somebody who's been programming for 20 years and thinks they have a pretty good handle on what their programs mean, then the rest of what you have to say is not going to actually go through their ears and into their brains. Do use arithmetic, draw an intuition of familiar things, add a non-trivial language feature. I know that I've already disallowed lambdas, continuations, and type systems, but there are some non-trivial language features you can use. And emphasize the need for an explicit mathematical model. So, for example, why do Bayesians, this is part of explaining semantics to somebody from machine learning. Why do Bayesians create models of processes? Well, reproducibility is one. We should be able to reproduce each other's work. That's good science. Formal manipulation. You might want to take that joint distribution and move some parts around. Proof of properties. You might want to prove that two parts of your model are independent and therefore you can do inference on them separately and then combine the results. Okay, so why do PL researchers create models of languages? Exactly the same reasons. We do slightly different things. Well, not slightly different things. We do different things with them, but for exactly the same reasons. This is some common ground we can exploit. We both believe that explicit is better than implicit. If you name something and give it a mathematical model, you can manipulate it. So, a semantics is a mathematical model of a language. So here's our language we'll start with. Starts with a grammar. This is just BNF. This is something that, as computer scientists, we all are familiar with. Our language has the natural numbers in it, which is not a very interesting language yet. So let's make it a little more interesting. We'll add addition, which is still not that interesting, but we'll make it interesting in a second. All right, so what should add 4, 5 mean? It could mean like 4 minus 5, right? Okay, we probably don't want to do that, but it's allowable. In general, though, we have two main options, an operational option. We can say that add 4, 5, what it means is how it computes. That's an operational semantics. It's like sitting down at the Python REPL, typing 4 plus 5 and getting a 9. Or we have a denotational option, and that is to turn our program into mathematics of some kind. And then we can reason about it using mathematics. That seems like a fine distinction right now. It's going to get less fine in a second. So, as soon as we add something a little more interesting to our language, non-deterministic choice. Choose just means choose between these two things. What should choose 10, 20 mean? Again, we have two main options, an operational one, either 10 or 20. It could be a faithful implementation of this semantics decides that it's 10 on Tuesdays and 20 on every other day. We don't know. We're not modeling how it makes the choice. We have a denotational approach we could take, and here's a good denotational approach. It could be a mathematical set containing all of the possible outputs for this program. We're going to go with that. To define a denotational semantics, we define a semantic function. And already it looks a little bit weird. It's got those double bars, you know? But it's just a function. It's an outfix function, like floor and ceiling and absolute value. You stick something inside of the bars in order to evaluate the function on some value. And it just happens to be a function that operates on syntax and gives us the meaning of that syntax. What should its return type be? Well, here's some guidance. We like uniform interpretation. Bayesian models, we always interpret them as a joint distribution. If somebody came up to us and said, here's my Bayesian model, and it means a prime number, we'd be a little bit worried about that person. So we should pick a uniform representation. In particular, we don't want the meaning of 10 to be a number and the meaning of choose 1020 to be a set. What we can do is make the meaning of 10 be a singleton set, and this will work just fine. So let's define the semantics.
So
it is, yes?
Why did you not say element of choose 1020 in the set 1020?
Let's see. Which side are you from, ML or PL? This could make a difference.
General computer science.
General computer science. So why didn't I say in 1020? We are really fond of equalities. They're easier to reason about than membership.
I imagine you could have a distribution with peaks at 10 and 20.
Yes, you could.
But that seems a bit advanced.
Well, if we did a distribution, then we would be saying something about the relative frequency with which things are chosen, and we are not saying anything at all about how they're chosen because we don't know. Does that make sense? You could totally do that, and in fact, that's kind of one of the reasons I like this example, because you can easily imagine extending it with probabilistic choice instead of non-deterministic. Did I do okay answering your question?
Equal there has any of the standard meanings of equal, whereas I think in would have the standard meaning of in.
No.
It's just definitions.
Yeah, it's definitional.
It's an example of semantic. So that is valid semantic.
I think you missed the part about operational, but you want.
No, I was there for operation.
Okay.
Anyway, let's move on.
We can talk about this offline afterwards and try to get it sorted out. Or it could be that if I show you more, then it'll just magically click or something. Shall we go on? Okay.
Andrew, the way I think about it is that the semantics is all you need to know about the expression, what its meaning is. So you want to know the whole set, 1020.
Maybe at the end I'll understand.
Okay. All right. So, well, maybe if we define the function, it'll help. So here's its type. It takes expressions as inputs, and then it returns a set of natural numbers. So this is the meaning of programs as the set of possible things they can return. It's defined by a few rules. So these are definitional equals. If just the meaning of a number is a singleton set containing that number, because that's the only thing that it could evaluate to if we made an actual programming language out of this. To choose between a couple of things means that we take the things that they could return to us and make a union out of them. Addition is a little bit more complicated. We have a nested union in here. It's basically just a doubly nested loop. So we loop over the things in, or the things in the meaning of E1 and the things in the meaning of E2 and add them together and then collect them all in a set. Some test cases, let's test it. Yes, 10. The meaning of 10 is a set containing 10, just like we wanted. The meaning of choose 1020 is the union. So all we do is copy this down from the semantic, from the definition of the semantics. So we copy it down, substitute E1 and E2. And then we can substitute further and then just manipulate it till we get a set of 10 and 20. Addition, copy the definition, and then inside here we still have the meaning of 4 and the meaning of 5, so we'll substitute those definitions to get the set containing 4 and the set containing 5, and now it's just computation to get the set containing 9. Okay, there is semantics in 5 minutes, well, at least denotational. All right, so our language actually has an interesting property that's kind of difficult to find in other languages, and that is a distributive property. If we add 4 to either 10 or 20, we'll get either 14 or 24, which is the same thing we'd get if we chose between adding 4 and 10 and adding 4 and 20. In general, for any program, E1, E2, and E3, this distributive property holds. Addition distributes over non-deterministic choice. Now, It's easy to see that using numbers. It's a little bit harder to see that, just kind of intuit it if you're thinking in terms of any possible expression or any possible program you could write in this language, which is why I like this. But you can prove this using the semantics. It's possible. Also, what if you added a new kind of expression to your language? Is it possible to falsify this property? Is it possible that this would no longer hold? Any PL people want to take a stab at what you might do to this language?
Expression of the same type.
Expression of the same.
I mean, it still denotes power set of n. You're not going to change power set of n to something else. Like I can't add exceptions.
Okay, yeah. So, or exceptions or side effects of some kind.
In operational semantics, you wouldn't have that.
Right. Okay. So, I was thinking in terms of side effects. So, a side effecting operation like a print, maybe.
Well, choose operational choose as a side effect.
Oh, yeah, that's true. Okay, different side effects. I was thinking in terms of more like mutation or something, because if you use this rule in a programming language that has side effects, the side effect would happen in two places, and then your property would no longer hold. Okay, reasons I like this example. It's easy to imagine implementing. It's a stupid language, but it's easy to imagine implementing it. It only draws upon knowledge of grammars, arithmetic, and sets, and maybe you have to get used to the funky meaning of notation. The distributive property is just non-obvious enough that you'd think, yeah, maybe I should go to the semantics to check it out and see if it holds. And it shows that semantics aren't just for running programs. Sometimes we want to do something else. We want to know something about a program instead of running it, and we can make a semantics to do that. And it's also easy to imagine replacing choose with probabilistic choice. Okay, so how do you explain probability to programming languages, people? This is something that I've struggled with a lot, okay? Because I have mostly been publishing my papers in programming language conferences. So, things to avoid, all your favorite stuff. Right, don't use these. Okay, again, philosophy, do not say these words, okay? People in programming languages have a very different idea of what it means to believe something than people in machine learning. So an idea that some probabilistic law could prescribe what you should believe about something is actually a little bit, yeah, okay, don't do it. Zero probability conditions, it means you have to talk about, I've actually been called out on philosophical issues with this and about how you derive Bayes' law for densities from Bayes' law for probability mass functions. It turns out that you can't without an extra axiom. It's very interesting. So anyway, avoid. Do. Use coin flips in uniform distributions. Everybody understands flipping a coin, and everybody who's programmed has, well, probably has used a programming language with random choice in it where you get a number from 0 to 1. Illustrate with physical processes, which we all have in common, and draw upon intuition for area and volume to explain what probability is. So here's an example that I gave in the context of probabilistic programming languages at ESOP earlier this week. Here's a probabilistic program. Not a very good one. It just flips a coin, and it names the result of it X and then returns X. Oh, okay. Well, so with half probability, we get Thomas Jefferson's head, and with half probability we get his tail, and then it's not very interesting, so let's flip another coin. And we'll call it Y, and because we're in England, we'll flip a pound coin, and with probability 1/2, we'll get the Queen of England's head, and with probability 1/2, we'll get her tail. Except I think she only has a tail in some episodes of Doctor Who. No, that's the Royal Coat of Arms. So I have arranged the outcomes of this program conveniently so that they take up the same amount of space on the slide. And you can use that to think about, that corresponds with their probabilities, okay? So each one has equal probability of happening. This is not an interesting program, again. In particular, X and Y don't have anything to do with each other. They're independent. So let's introduce some dependence. We'll make it so if we flip the first coin and get heads, then we'll flip the second coin, we'll flip a fair coin for the second one, and otherwise we'll flip an unfair coin that has a 0.3 probability of being heads. And our output space now looks like this. Now, critically, even though we've changed the program and done some weird things, introduced some independence, it still satisfies something called the law of total probability, which is if you add up all these areas, you get 1, always. The probability of getting the queen's head is the sum of the probabilities of all the outcomes in which you get the queen's head. That's pretty straightforward. Now, here's something that Bayesian statisticians love to do. They love to restrict their attention to just one part of the probability space and reason about just that one part. Okay? So, for example, we might say, given that we saw the queen's head, what's the probability that we got Thomas Jefferson's head? Now, because we're not dealing with the entire probability space, in order to answer this question, we need to renormalize. And so we divide by the probability of getting the queen's head, and we can answer this question. And it just so happens to not be 0.5. It was, the original coin was flipped with probability 0.5, but by restricting our attention to part of the probability space and asking the question, we get a different answer. Or in the Bayesian philosophy, by observing that we got heads for the second coin, that tells us something, we learn something about the first. That's Bayesian inference. Here's another one of my favorite examples to illustrate probabilistic reasoning. So, stochastic ray tracing. Stochastic, really this just means that we're doing it in a physically based way. We're going to simulate physics. So imagine we're in a room with a single light source and it's just sending photons everywhere in random directions, uniformly random. Now imagine the percentage of them that actually go through your pupils. That's very small. It's vanishingly small. And, but those are the ones we're interested in. Those are the ones that make a picture on the back of your eye that your brain can interpret. So we really only want the photons that go through an aperture. Which is an event that happens with some very, very small probability. Now, we actually want this aperture as small as possible, too, because the smaller it is, the more focused our result is going to be. We'd really like to do something like this, where we only simulate the ones that actually go through the aperture. This is what a stochastic ray tracer does. Then it sends them all back onto a virtual screen and collects them to form an image. Now, it's critical that when we filter these things out, or that when we sample in this way, that we maintain the probability, the original probabilities, in some sense, of the original photon paths. Because if we don't, we'll get garbage, or we'll get something that's worse than garbage. Have you ever actually watched this? I couldn't get through it all. Okay, so what I like about this example is that it's visual. It draws on intuition that we have about physical things. It motivates conditioning. Why are we restricting our attention to this tiny part of the output space? Well, because we want to form an image. It illustrates how rare events make things hard. It's really easy to imagine that, oh wow, we only want that vanishingly small proportion of them? Yeah, that is hard. And sometimes we want that probability to be as small as possible. It shows why the conditional distribution matters and not just the values that get assigned probabilities. And it motivates sampling methods. It makes them look like the obvious thing to do, which sometimes in explaining probability to people in programming languages is a hard thing to motivate. It also motivates probabilistic programming languages. A hand-coded stochastic ray tracer is thousands of lines of code that don't look anything like the physical process that it is simulating. Because that constraint, the photon path must pass through the aperture, is weaved in through the whole thing. It's kind of like it like infects the program. And from a personal standpoint, it allows me to distinguish my own work because, as far as I know, I have developed the only probabilistic programming language in which you can actually code it up that way, or in a nice way. So in Dr. Bayes, which is the one I am developing, it's still just a simple physics simulation. This is the most complicated part of Dr. Bayes, not Dr. Bayes, the most complicated part of the simulation. The rest is basically a vector math library. In other probabilistic programming languages, it's either not possible or it's just as hard as in a general purpose language. In Dr. Bayes, you just say, this is the physics simulation, give me all the photon paths that go through the aperture. And in other ones, you can't do that. Now, my first probabilistic programming language? No, I got stuck way earlier on the simplest things imaginable. Max 0.5 random. This is my favorite example of something that's difficult to do, but it seems like you should be able to do this, right? It's not because that people who implement probabilistic programming languages aren't good at it. I know these guys, they are very smart, but the reasons are almost entirely theoretical. Let me explain why. So, we have a random function that we can call, and because of course we're doing a Lispy language, you put the parentheses on the outside, and it returns a value uniformly between 0 and 1. Now, to quantify the uncertainty here, to give it a distribution, we can use a density function. Now, the density function doesn't give us the probabilities of outputs, because if it did, then the probability of every output would be 1, and if we tried to sum them all together, we would get infinity, and they're supposed to sum to 1, according to the law of total probability. What a density is a change in probability. It's like a derivative, and so we have to integrate to find actual probabilities. If we want the probability that random returns a number between 0.5 and 1, we need to integrate its density from 0.5 to 1, and we get 0.5. Now, critically, if you try to integrate it on a single value, you will always get 0, because there's no function you can integrate between a and a to get anything but 0. It's just how integration works. So let's look at max 0.5 random. It looks a lot like random on the right side, as it should. And on the left side, it never gives us anything between 0 and 0.5, so there's no density there. But what about at 0.5? So what it does is take all of this function, you can think of it as taking all the probability between 0 and 0.5 and piling it onto one point. And so what we'd really like is this. We would like the probability of max 0.5 random to be on this singleton to be 0.5. But we know that if we integrate any density from a to a, we get 0, and so this density can't exist. Ooh, okay. Well, here's our first technical gap. We have a limited theory probability that we typically use when doing probabilistic modeling.
Excuse me.
Yes?
Could you go back to the previous slide and talk to me like I'm a programmer?
It's not programming. Let's see. Talk to you like you're a programmer. I'm not sure what you mean. Can you ask a more specific question?
I mean, what exactly is the problem again with the max 0.5?
Okay, so max 0.5, it takes anything that's below 0.5 and makes it 0.5. Okay, so
You haven't said what max 0.5 random should return.
Distribution whose every value is sampled is
Yes, but he hasn't said that.
Yeah,
So
so
what type of this function?
the type, it's a real number from 0 to 1.
No, lambda nothing max 0.5 random.
Lambda nothing max 0.5 random. Yeah, okay.
Right? What does that return?
That returns a real number between 0 and 1.
Distribution.
Right, okay. So, right. So it depends on whether we're thinking operationally or denotationally. If we're thinking operationally, it returns us a number. We're thinking in terms of an implementation. If we're thinking denotationally in terms of mathematics, it means a distribution. Yeah.
for which you have Dirac.
Well, I mean, operationally, you can imagine it, you're running it many, many times.
Yeah, you can. And half the time you get 0.5, and half the time you get something between 0.5 and 1.
Why can't you have Dirac?
Good question. Okay, so the strict mathematical answer is that those functions are just a formal device and they don't actually exist. It would be really interesting to try to formalize them. I can give you better motivation than that, though. On this slide, in fact.
But they do exist in distribution theory. It's Laurent Schwartz, etc.
That's a thing you mustn't say to programming language people.
Right. Okay, well, let me show you these other problems first, okay, and we'll see what other things densities can't model. So I talked about discontinuities, and this is very interesting to me. That if you're Bayesian and you want to model a thermometer, and the fact that it can't show you anything below 0 and anything above 100, you're kind of hosed. That's fascinating. Variable dimensional things. So if you have something that says flip a coin, and if it's Heads? No, if it's true. Wow, my coin flip got different. If it's true, return a list with one random thing in it, and otherwise return a list with two random things in it. There's no single density function that describes the distribution of this. So the Dirac delta function wouldn't help you with that. Another thing it wouldn't help you with is infinite dimensional things. There are no density functions for infinite dimensional things in general, no non-trivial ones. And that makes it really hard to describe the distributions of streams, and when you get into the guts of making a programming language, recursion or unbounded loops. In general, densities are just insufficient to model the outputs of probabilistic programs. And you have to restrict your language quite a bit to use them. There is a theory that handles everything, but it's extremely general. And when I went to the, so I went to the math department to take courses on it, measure theory, and they never computed anything. Well, they're mathematicians, that would be dirty. So it's really hard to find any computational content in measure theory, and I actually spent about 3 years trying to find it before I finally found some that was effective. But we need to talk about it because this is the only way that I know of, and really anybody knows of right now, to get around this problem of densities not being expressive enough. So a probability measure is kind of like a density that's already been integrated for you. So let's take the measure of random, the uniform measure between 0 and 1. So it maps subsets of the unit interval to probabilities. And it's defined this way. So we can define it using just intervals and count it as defining pretty much any possible subset of the unit interval that we could write down. We can define it using integration, but we don't have to because this is a measure. This is a primitive concept. The measure of max 0.5 random is this. It actually exists. And if you squint hard enough, you can see where it comes from. This max 0.5 b minus max 0.5 a, that is a lot like b minus a. It just happens to all happen above 0.5. But in particular, this is the interesting part. This term here assigns probability 0.5 to that singleton 0.5, which is the thing that the density could not do for us. So to bridge the gap, this technical gap, we need to derive measures from code and then somehow compute them. Here's how I've chosen to do it. This is the way I finally discovered. So we're going to interpret max 0.5 random as a deterministic function that takes a random source and outputs a value, and define it this way. So this is our random source. It's a uniformly random number, and the function is computed in kind of the obvious way. So Haskell programmers in here? Anybody program in Haskell? Okay, this is just like the random monad. Okay, this is no different, except this time, instead of a stream of random numbers or a random generator, we have just a single uniformly random number, just for simplicity's sake. To derive the measure of max 0.5 random, we can do this simple thing. Well, maybe it's not that simple. It's defined in terms of the probability measure over the input space. And we compute this, f to the minus 1 of b, which is a preimage. A preimage is all the points, this will give us all the points in our input space that would produce something in our output. So in other words, to get the probability of a set B, we find all of the inputs, all of the random sources R that when we apply F to them would give us something in B. This can be factored into nice parts. It factors nicely into a random part and a deterministic part. And one thing I really like about this is with PL people, this means that if we concentrate on this, we can entirely forget about probability. It's all just sets. So in other words, we can compute measures of expressions by running their interpretations backwards on possibly uncountable sets, which might seem like a tall order. All right, well, what about approximating? So here's a preimage that comes up in some of my tests. This is, if you really want to know, it's the normal model with a circular condition, which I think is kind of fun. It looks like a football. It is not linear in any way, so linear approximations aren't going to do very well. But we're going to try some kind of approximation anyway. What if we approximate with rectangles? This is a sound approximation of the preimage, and it is not helping us very much. There's a lot of empty space that this covers, and so its measure or its area would be very different than the area of the actual preimage that we're trying to measure. And if we sampled inside of it, we'd mostly miss. the pre-image. But what if we cut it in half? We could cut it in half and then restrict the interpretation of our program to one half and then the other and compute pre-images just on those halves. It would shrink. And then we could, I'm going to call that refinement. We could split and refine and split and refine and split and refine, split and refine, and it's getting closer and closer. This is a fairly good approximation of the pre-image. If we measured it, it would be pretty close. Now this doesn't scale very well. So in Bayesian inference, we like to have 100,000 random variables, and this is an exponential time algorithm. 2 to 100,000 is not good. But there are techniques that scale, like sampling techniques. So what if instead of enumerating all of these, what if instead of splitting and then choosing both halves, we just chose one or the other with some probability? Then we could sample from them, and from inside each of those, we could sample a point. If we did that enough, we would get samples just inside of this pre-image. Okay, this brings up an issue. This brings up a cultural issue, a pretty big one. Sampling is difficult to swallow. All right, so early on, when I joined Jay's lab, he asked me to just write something. I was taking a long time learning measure theoretic probability, and he needed me to write a paper just so we could get some practice and so he could see what my writing was like. And so I chose to write on probability is the only good way to model uncertainty and how sound approximations don't scale, but sampling does. And his review was basically this. Now, I had run headlong into some philosophical differences between us. Our ideals and motivations differ significantly between programming languages and machine learning. In programming languages, 5 nines is not enough. We must have complete certainty. In machine learning, usually 99% certainty isn't feasible, okay? You're lucky to get 95. Programming languages, only sound approximations are admissible, and we have to provide guarantees. And in machine learning, they've learned from long experience that logical reasoning doesn't scale to real-life problems, so we can't provide guarantees. In programming languages, correctness on all inputs is desirable and achievable, and in machine learning, perfection in one domain usually implies poor generalization. See the need for bias in learning generalizations by Mitchell. The problem is all of these above statements are true in context. In our own specific research domains, they are all true. Let's look at the contexts. So here's a silly example I came up with. Let's say that you were writing a language for writing, creating a language for writing end-user license agreements. I'm not saying this is a good idea. I'm just saying it's something you might do. All right, so you can have named entities in it, such as the software and Acme Corporation, and it's based on well-known research on contracts by Findler et al. The compiler creates daemons that answer questions. Anything on the system might ask the question like, am I allowed to copy this file? Does it violate the end-user license agreement? Am I allowed to send this, like the network stack might ask, am I allowed to send this personal data to Acme Corporation? Now, the query language has to be meticulously defined so that you can ask very precise queries, and soundness means always denies a contract-breaking action. It might deny something that is not a contract-breaking action, but you're really after not breaking the contract. And then it becomes used as a target language for compilers for all kinds of human contracts like rental agreements and marriages, and then people install it on their phones, and it ushers in the Big Brother apocalypse. So this is what our research context is like in programming languages. We work on well-defined problems, and if our problems are not well-defined, we add definitions until it is a well-defined problem. Our languages tend to be used in the middle of a giant pile of abstractions. Like this end-user license agreement language became a target language for other kinds of things. JavaScript is now a target language for compilers, which is a little bit scary, actually. So, I mean, how do you keep this big pile of abstractions from falling down? Okay, so because we work on well-defined problems, we can get correctness, and because our languages are using this big pile of abstractions, to keep them from falling down, we have to provide guarantees to the things above them. All right, let's look at the machine learning version of this. We're going to create a classifier that determines whether actions violate Acme's end-user license agreements in particular. So we could use keystrokes as data sources, hard drive contents, running processes, the webcam. We could use some recent research on emotion recognition in faces to see if somebody's doing something sneaky. And of course, we need examples of users violating and not violating the end-user license agreements and what was going on the computer so we can train the classifier. We would handwrite a watchdog daemon that tries to determine when the users were breaking the contracts, and it's correct whenever it reports a real violation. The system is clearly AI complete, and that's dangerous. So here's the research context for machine learning. Ridiculously under-constrained problems. It's amazing how under-constrained problems you guys did. You know what, I'm a machine learner too, that we tackle, okay? The algorithms get used near the top of the pile of abstractions, not in the middle of it. And so correctness is almost never achievable. But we can make some strong assumptions that give us good performance, and we can tolerate errors because our stuff is used near the top of the pile. So now this is one of the most difficult gaps to close, I think, because whenever you do research in probabilistic languages, you need to satisfy both sides, and they're both pulling at you with their ideals. So the programming language ideals that you need to provide guarantees and the machine learning ideals that you have to provide approximations at scale are both kind of difficult to meet at the same time, right? So here's how Dr. Bayes does it. Well, either satisfies or dissatisfies both sides by compartmentalizing them. So at the very bottom, there's an interpretation of programs as pure functions that operate on random sources and return some value. And this is assumed correct. This is our baseline. Built upon that, there's a preimage semantics that interprets programs as functions that compute preimages, and this is proved correct with respect to this semantics. In other words, if you give these two semantics the same program, then this will return something that computes preimages under what this one returns. Now, because these things are horrendously uncomputable, they need to be approximated. I use rectangles currently. So there's another semantics that outputs things that compute approximate preimages, and this is proved sound with respect to the correct semantics. So that, yeah, I'll show you why in a second. Now, in order to implement it, I needed a rectangular set library, a way of doing something like interval arithmetic, but in reverse, and this is also sound. And then we draw a very dark line that we do not cross. It is the soundness barrier. And on top of the soundness barrier, or on the other side, we have sampling algorithms which converge in probability. This is the best way I've found to resolve the tension. There are guarantees on the bottom, exactly the kind of guarantees that we like to see in programming languages, and there's scalability on the top. Okay, so motivating soundness to somebody in machine learning is actually pretty easy. You just need to show them something that it enables that is useful. So, Dr. Bayes' way of approximating preimages by using rectangular sets and then sampling from them, and then sampling inside of them is one way to do that. Convergence of the sampling algorithm requires that the approximating preimage semantics be sound. If it weren't sound, there would be places inside of the preimage that it might miss. There would be places that would never get sampled from, and so the sampler wouldn't converge. Motivating unsoundness to somebody in programming languages, I think, is significantly harder. It's harder to get somebody to loosen their, what's the word I'm looking for? Their standards. So, in fact, I had this conversation with my advisor just last week. I asked him when, if ever, he accepted sampling as a viable way to represent the meaning of programs. And he gave me this answer. Now, I actually call this a win, actually. I don't think I will ever convince him that sampling is a worthwhile thing to do, but he trusts me, and that's okay. Now, even with somebody like Jay, who will probably never accept sampling, you can start small. There are people out there that want this sampling stuff. It's kind of weird, but this is what they want, and we can give it to them. Yeah?
Does Jay like quick check?
Yes, Jay likes quick check. That's the thing. He likes fuzz testing and randomized testing. I think it's, I'm not sure why that is. I need to nail that down. All right, so now we get to the difficult part, and that's when we have to talk about prejudices. preconceived opinions that aren't based on reason or actual experience. They are really easy to develop, and all you have to do is take a good ideal or a good attitude or a good anything in one context and apply it without conditions in another. So for example, it's really easy to start with we must provide sound guarantees and go to sound approximations are the only useful approximations. And it's really easy to go from I know what my programs mean well enough to write great programs to semantics are unnecessary. These are not good implications. We can't actually conclude them, but we do because I think we overgeneralize. It's just easy to do. How do you address it? I have not found great ways to address these yet. Sound approximations are the only useful ones. There is overwhelming evidence against this, at least at the top of the abstraction stack, not in the middle. In the middle, you must provide guarantees to the stuff above you or the entire thing falls down. I used to have floating point on this slide, but then somebody at the last place I gave this talk to said, no, we don't believe in floating point. And most of them agreed. That was very interesting. So semantics are unnecessary to make a probabilistic language. This one is probably a little bit easier. Start with reminding them of the paradoxes. Statistics is full of these paradoxes, these weird, unintuitive things that happen that when you dig down into it, you could figure them out, but until then, you're like, whoa, why did that happen? This is the conclusion I make from that. If you iterate on a probabilistic programming language until it never surprises you anymore, you're probably doing it wrong. It's got errors in it somewhere, because statistics should surprise you occasionally. All right, so in fact, I've got a new one for you. This one's fun. I discovered this while making Dr. Bayes. It doesn't allow zero probability conditions. I'm almost finished, so it's good. You have to use intervals instead of equality constraints. So here's a standard normal model with two observations. So we have x distributed normal 0, 1, and y1 distributed normal centered on x, and another one centered on x. And we condition x on this being true. Whoa. Y1 has to be between something near 2 and something else near 2. So y1 has to be near 2, and y2 has to be near -1. So that's like saying y1 is equal to 2 and y2 is equal to -1. Except with a small interval. Now these epsilons, epsilon 1 and epsilon 2, control the width of the intervals, and it seems like they should at least be proportional to each other or something, or they should be equal. But it turns out that doesn't matter at all. That's weird to me as a statistician. I would expect the narrow interval to make more of a difference, to be weighted higher in the evidence or something. So here's the true density for this model, the true posterior density. And so with epsilon being 0.2 and epsilon 2 being 0.01, the estimated density from the samples is almost exactly the same, both ways. And if we look at the pre-image space, they look different. Like, on the right side, it's wider on this one. On the left side, it's wider on this one. But they give us pretty much the same distribution of samples on the other side. The width matters a little, as long as you get it small enough. But proportionality doesn't really matter at all. That's strange. Okay, the general property is actually due to something called the Lebesgue differentiation theorem. You can go and prove this, which is kind of nuts. All right, so speaking of sampling, here's a technical gap. Probabilistic program distributions are weird. Compared to distributions you encounter in regular machine learning, they are strange. So for example, one point on the support of the distribution of program domains is an infinite tree in Dr. Bayes. This is its source of random numbers. How do you sample from a source of random numbers, especially when you're doing Gibbs sampling? Wow, okay. The current inference algorithms are developed for very different distributions, nice rectangular or Cartesian product-y kind of things. On the other hand, probabilistic programming languages can provide a lot of extra information to help these things out. But algorithms is one place where there is a big gap that we need to fill to make our probabilistic programming languages work. So, in summary, when I moved from machine learning to probabilistic languages, it was a big culture shock because of the cultural gaps. Vocabulary, formalisms, ideals, motivations, even prejudice made it very difficult to communicate, to get along, to collaborate, and these gaps keep us from working together as people who do machine learning and probabilistic languages, but they can be closed and bridged. Probabilistic programming languages are hard to create because of technical gaps, but limited theory of probability. I didn't get to talk about limitations in programming language formalisms that I've had to overcome, but I did talk about our existing sampling algorithms and how they kind of struggle. But these are the gaps that are the opportunities for us to do foundational research. And if we can close the culture gaps, we can work together and make this happen. Thank you.
Thanks so much, Neil, for a very interesting talk, very insightful. I think we've got time for one question because we have another talk coming in at 2.
Right after this. Yes?
So it seems like you're dealing with the case where your if I can use machine learning terms, your posterior has some sort of limited support, right? So there's only some possible regions of your original parameter space that could lead to the observations that you see.
Well, that's one case I'm interested in. In general, I'm interested in the cases that you can't model with the density, which are, were you here for the beginning of the talk?
Yeah, I was here.
Okay, yeah.
I guess I'm asking about your rectangle strategy, and so you've sort of drawn this limited region, which is where the support is in the posterior, but in most problems, the whole space will be the support.
Actually, in most problems, it's still one little tiny stripe. It just happens to be along an axis, and you can forget about the other dimensions, the ones that you observed. So it's still very sparse.
Logistic regression model, that's not going to be the case.
Yeah, we can talk about that afterward. I can draw some pictures, and that would make more sense. I can't draw pictures right now. All right.
Let's take that offline. Great. Let's thank Neil again.